Let's take a look at binomial heap union h1 comma h2. So first is we are making the binomial heap h. We are making the binomial heap as h. Head of h is binomial heap merge h1 comma h2. So we are calling the binomial heap merge function. Free the objects of h1 and h2 but not the list they point to. If head of h is equivalent to nil, we return the h. Then previous of x is equivalent to nil. X is equivalent to head of h. Next of x is sibling of x. Right? So we are accessing three elements at the same time. The head of s, the sibling of x and the next of x. And while next of x is not equivalent to nil, we will check the degree of x and degree of next of x. Right? And then we have created the previous of x as x and x as next of x. And we can unite previous of x and next of x using this procedure. So else if key of x is lesser than key of next of x, what we will do? Sibling of x is sibling of next of x. Otherwise we will call binomial link next of x comma x. Else if previous of x is equivalent to nil, then head of h is equivalent to next of x. As I told you in the example, sibling of parent of x, previous of x is equivalent to next of x. Binomial link x comma next of x. X is equivalent to next of x is equivalent to sibling of x. And we need to return h in this case. So this is the algorithm for binomial union operation, binomial heap union operation, and this is very important from the examination point of view. Next topic is Fibonacci heap. The very next topic is Fibonacci heap. What is a Fibonacci heap? Let's take a look first. What is Fibonacci heap? Its Fibonacci heap is a data structure for priority queue operations consisting of collection of heap ordered trees. Fibonacci heap is a data structures for priority queue operations that consist of collection of heap ordered trees. It has a better amortized running time than many other priority queue operation data structures, including the binary heap and binomial heap. It has a better running time than many other priority queue data structures, including the binary heap and binomial heap. A Fibonacci heap is a collection of trees satisfying the minimum heap property. So it is a circular doubly linked list. Removing a node takes O of 1 time. It is a circular, Fibonacci heap is a circular doubly linked list form. And it's a collection of trees satisfying the minimum heap property. So what is the difference between Fibonacci heap and binomial heap? Extract min from Fibonacci heap takes O of 1 time. Extract minimum from binomial heap takes O of 1 time. We have extract min operation. Merge without any order. Merge in reverse order. Here there is a union operation. Here it is a consolidation operation. Union takes place in binomial heap and consolidate operation takes place in Fibonacci heap. This is an example of Fibonacci heap. You can see here this is an example of Fibonacci heap, that's 7, 3, 7, 18, 52, 38. That is how the Fibonacci heap looks like. Next comes the extract minimum process of Fibonacci heap. Let's suppose we have this Fibonacci heap with us. What is the minimum value out of these all the value? 3 is the minimum value. So the x pointer will points to 3. Whenever we access this 3, so the pointer would move on to the 17 pointer. So when we remove 3, all the elements of 3, 18, 52 and 38 would be arranged in this manner only. And the x pointer will points to 17 only. Now, what maximum degree is log to n, where n is the number of nodes. What are the different number of nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What are the different number of nodes? 15 number of nodes we have. So what is this index is of size 0 to 3. right? 0, 1, 2, 3. 0 size, 1 size, 2 size, and 3 size. So 17 is of degree 1. So one pointer would be points to the 17. 17 node have degree 1. So 1 would be point towards the 17. Next x comes to this. That is a 2 pointer. So 2 will be points towards the 24. You can see here 2 points towards the 24 in this case. Next comes this 1, 2. Next pointers change. Now 2 is also already occupied, so we can make merging operation between this 2 degree and this 2 degree. So we can apply consolidate operation and we can merge this. Now this is of 3 length. We can next, this is 0 length, this is 1 length, and this is also of 0 length. This is also of 0 length. So we need to merge 52 and 21. You can see here 21 and 52 is merged. Again we will apply pointers and again we will call the consolidate operation function in Fibonacci heap. This is the final Fibonacci heap. This is the final Fibonacci heap we have when we access the extracting the minimum element in a Fibonacci heap. When we are extracting the minimum element from a Fibonacci heap, then this is the final tree we have. Now let's suppose we are inserting a key in a Fibonacci heap. When we want to insert a key in the Fibonacci, let's suppose we want to insert 21 in this particular tree. So we can simply insert 21 like this, right? Like you can see here, we can simply insert 21 in this. Now again the number of nodes is equivalent to this index set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 21st node is 15. So we have index from 0 to 3. So again we will apply the consolidate operation function in Fibonacci heap to join this, to make a single degree binomial tree in the final Fibonacci heap. We cannot have two binomial tree in a Fibonacci heap with the same degree, as in the case of binomial heap as well. In binomial heap also we cannot achieve two nodes with same, or we can say two binomial tree with same degree. We cannot have this in the final binomial tree or in final Fibonacci heap. So we apply consolidate operation in this. So 2 pointer, 0 pointer, 1 pointer, 2 pointer, merging between these two, then 0 pointer, and we can easily merge these nodes using consolidate operation function. So we will simply apply consolidate function. Next is decreasing a key from a binomial heap. How can we decrease a key from a binomial heap? Let's suppose we have this binomial heap and we can decrease 15 by 1. So we can replacing 15 by 1. So this is 15 would be replaced by 1. You can see here in the diagram. So y would be this and z would be this. So we are comparing z does not equal to nil and key of y is less than key of z. Yes, key of y is less than key of z. When key of y is less than key of z, we swap these two lines. Right? So y would be, we have swapped these values, and y would be z and z would be parent of y. Right? Again we check the key of y and key of z. There will be swapping. So 4 would go here, 1 would go here. Like in this example, 4 would go here, 1 would go here. So now the final Fibonacci binomial heap is this. So we are decreasing the key in the binomial heap and we have decreased 15 by 1 and have created the final binomial heap. Let's check the algorithm. Binomial heap decrease key. H is a binomial heap. We are decreasing x by k. X is the node to be decreased and by value k. If k is greater than key of x, If k is greater than key of x, we can give error because we are decreasing the key. Key of x is equivalent to k, we have assigned the value. X is equivalent to y, parent of y is equivalent to z, we have assigned y node and z node in the previous example as well. While z does not equal to nil, key of y less than key of z. If key of y is less than key of z, we exchange key of y and key of z. Then y would become z and z become parent of y. As we see in this example, that again and again y and z would change. First of all, y would be this, z would be this, then y would be this, z would be this. If the degree of this particular binomial heap would be more, then we will again keep on doing this unless and until we have z is not equivalent to nil. Because after this step, when z is this, next step is z is equivalent to nil, because z would be parent of y and y is automatically changed in every path length. Fine. So this is all about binomial heap and Fibonacci heap. That is very important from the examination point of view. Fibonacci heap operations are consolidate operation, decreasing a key value. Binomial heap important are uniting two binomial heap and decreasing a key from a binomial heap. These are two very important topics in binomial heap and Fibonacci heap from the examination point of view. Thank you for watching.